Hello everyone, welcome back to this week's algebraic graph theory seminar. This week, Daniel, he's going to talk about quantum symmetries of Hadamard matrices.
Okay, thank you. Thank you for inviting me to talk on this seminar. So I will talk about my last results about quantum symmetries of Hadamard matrices. And since I was talking about this already once on an online seminar in January, and I thought there might be a slightly overlapping audience, I decided to alter the talk a bit. So I was also told that many of you are already familiar a bit with quantum symmetries. So I will introduce the quantum symmetries just briefly, and then I will focus on explaining more the proof of the main result, which is about Hadamard matrices, although I will explain it on a slightly easier example. Right, so, and the main tool for this are so-called diagrammatic categories. So first, how this works. Well, usually we start with some vector space V. So let's say some Cn, and we will study what physicists would call tensors, so some linear maps from between some tensor powers of this vector space V. And so such a linear map can be like, for instance, some A from V tensor V to V, or some B from V to V tensor V. And so, for instance, this A, this is a linear map that takes two vectors and gives you one vector. So that's sort of like a black box, which has two inputs. You put the vectors into that inputs, and you obtain one output, one vector. And the same works with B, but just you have one input and two outputs. And the point is now that with this notation is convenient to describe some operations with these operators. Like, for instance, A composed with B, what that means? Well, this means that I have one input. Well, I first put it into B. This gives me two outputs, and you can think of really as wires, and you plug those wires into the other black box, denoted by A, and this gives you one output. And this is how it works. First you use B and then A. Well, and you can do the same for B composed with A. So this means that you first apply A, you have one output, and then you apply B. But you can also do other stuff, like, for instance, you can put A and B side by side. So you have here two inputs, here one input. And in total, this is, again, a diagram which has three inputs and three outputs. And what does this diagram describe? Well, the first two outputs go to A and the other one go to B, and they are not mixed anyhow together. So this is just a tensor product, A tensor B. And finally, if you want, you can also do some conjugation. So I will denote the conjugate transpose by dagger, and this goes just the other way around. So from V to V tensor V. So this is something like that. But you can also do more complicated stuff, like you can take this A, this has two inputs, one output, and for this one of those inputs, you can again use, for instance, an output from another A. And I don't know, you can put the B here, for instance, and now maybe you can use those two outputs for, let's say, B dagger, and so on. So it allows you to describe these compositions in a diagrammatic way. And what I will often refer to will be what I will call category generated by A and B. And what I mean by this is the set of all linear maps that can be created from A and B using these operations of composition, tensor product, and involution. So by the way, if I say category, I always mean a monoidal category with monoidal Dagger category. So I not only have the composition, but I will always have also the tensor product and the involution. Well, and the point is that all these diagrams I drawn here, all of them are by definition elements of this category because they are formed using these operations. But also on the other hand, this category exactly consists exactly of the linear maps that can be written as such diagrams, or maybe they are linear combinations. Right, so this is precisely what this category means. And now what we are going to use this for are quantum symmetries. So briefly, what are quantum symmetries? Well, usual symmetries are described by groups, and typical groups are given by some relations. So for instance, orthogonal groups is a group of all orthogonal matrices. And being orthogonal means just this thing. Everybody knows that. And so what are quantum symmetries? Well, for me, a quantum orthogonal matrix would be, again, a matrix whose entries satisfy exactly these relations. But now the entries of the matrix itself are allowed to be elements of some non-commutative algebra. So they can be itself some matrices or some operators on some Hilbert space, on something like that. And well, and technically we describe that using an algebra. So this ON plus, this is called the free orthogonal quantum group. And it is described by an algebra by a universal. Here can be either a universal C-star algebra, or if you don't like C-star algebras, you can just use ordinary, just algebraic algebras. And that's and the entry. Well, the algebra is generated by some elements Uij, which stand for the matrix entries of my big matrix U, and these entries, those generators, are supposed to satisfy the same relations as ordinary orthogonal matrices. Well, and by the way, why do I use this notation? Well, if you studied the algebra of continuous functions over the orthogonal group, which is denoted by C over N, then this would be the same algebra, except that you would, in addition, have commutativity here. And, well, if you forget about commutativity, you get what is called a free orthogonal quantum group. So somehow the non-commutative version of that. Well, that's somehow the idea, and you can do this for all other groups you want. So for instance, you have the symmetry groups, so group of all permutations, and you can define the quantum counterpart. So here, well, permutations can be described by permutation matrices, which are matrices with entries 0s and 1s. So this is the fact that the entries are just 0s and 1s is described by this relation. And in every row and every column, there is exactly one, otherwise there are 0s, which is described by this relation. And this is just directly translated to this non-commutative version. you might be also interested in symmetries of graphs, which are just permutations that in addition preserve the adjacency. So they commute with the adjacency matrix. The permutation matrices commute with adjacency matrix, which is the additional relation I have here. And now an important thing is that all the relations I wrote here are actually of the form that the matrix here, this U, commutes with something in some sense. So here with this adjacency matrix, it works like directly. So it's supposed to commute with the adjacency matrix, which is because we require the action of the group or the quantum group to preserve the adjacency. So it should preserve the adjacency matrix, and therefore it should commute with that. But all the other relations are also of this kind, because always you are building the group in that way that you want to preserve something. For instance, with this orthogonal group, you want to preserve some bilinear form. So you have some bilinear form beta from V tensor V to C, which is just given by delta ij, and this is what you want to preserve. So actually your relation, I could write it this way, that the action of the U preserves this bilinear form beta. And if you really write down this relation, it's just the orthogonality. And the same holds for the symmetric group, although here it's not that obvious. I will explain that later. But again, those relations are sort of commuting with something. And it actually turns out that for groups and also for quantum groups, not only those defining relations, but all relations are of this kind. So what I mean by that is that you can take a group or a quantum group, and you can consider all linear maps between tensor powers of the vector space where the group acts, and all such linear maps that commute with the fundamental representation this way. So those are called intertwiners in the representation theory, right? And the point is that, well, this set forms a category. So what I mean by that is that if you compose two intertwiners, that's again an intertwiner. If you make a tensor product of two intertwiners, it's again an intertwiner. If you compute a conjugate transpose of an intertwiner, it's again an intertwiner. So this is a category, and conversely, if you start with a category, monoidal, take a category with some axioms, you can reconstruct the quantum group. So if you want to study quantum symmetries of something, or ordinary symmetries of something, instead of studying the group or the quantum group, you can just study the category. And the category, what kind of category is that? Well, there's a category that's generated by sort of like the stuff you want to preserve. So if you're studying symmetries of some algebraic structure, you want to study the category which is generated by the structure maps. So, right, that's it. So that's the idea. And let's have a look on concrete examples. So the easiest example is probably just symmetries of a finite space, which is classically the permutation group. So, right. So what is this finite space? A finite space, I mean, just a set of just n elements. And this set of n elements well, there's just a set, and well, as you can see, I'm always working with some vector spaces. So I need to act on some vector space. So how do I make a vector space out of a set? Well, I sort of like take an n-dimensional vector space, right? Or what I could also do, and what we usually do when we are studying those quantum structures, is that I study again the algebra of functions over that space, which is a finite dimensional C-star algebra spanned by the canonical projection. So those are the functions that work like this. And right, but okay, so this is a vector space. Well, this is my vector space V, as I always use here, but it's not only a vector space, that's an algebra. So in addition, I can multiply the functions here. I have the delta I times delta j is delta ij delta I. So so all in all, I have a multiplication, which is a linear operator, or a linear map that takes two elements of this vector space and gives you another element of this vector space. So I have, well, such a black box with two inputs and one output, right? And actually, for some reason, it is also important that this algebra has is equipped with a bilinear form. And so I can define this in the obvious way, bilinear form taking delta I times delta j equals to delta ij. Well, so this is again a map from V tensor V to the complex numbers. And again, that's just black box with two inputs and now no outputs. So since the outputs are just scalars. And my question is now, well, what I tried to explain earlier is that the quantum symmetries of this space is described by category generated by the structure maps, by the multiplication and the bilinear form. And so what is this category? Well, at the beginning, it is not at all clear, right? So there's infinitely many ways how can I compose this M and this beta together with those tensor products and involutions and so on. So it's not at all clear how large this category is, for instance. But I can use the diagrammatic approach. But, well, using the diagrammatic approach, how is that helpful? Because, okay, again, if I fix the number of inputs and outputs, there's infinitely many of diagrams involving this M and beta that can be constructed like that. Well, so what we can use, well, first of all, it's convenient to introduce a convenient notation. So what I will introduce are those so-called spiders. So I will introduce such diagrams. Here are K inputs and L outputs. And this is just a black dot or blue dot. And this will stand for some linear operator between kth tensor power to lth tensor power. And, well, how this operator will act, well, let me just give the action by specifying the matrix entries or the tensor entries. So it has K plus L indices. And I will define it to be given just by canonical delta. So all of the indices have to be the same. Well, why is that convenient for me? Well, because this multiplication, this is just such a spider, this beta, this is just such a spider. Okay. And so what is the category generated by these? Well, first, let's have a look on what is a category generated by all the spiders. And this category, what does this category contain? Well, this category contains all pictures that look like this. Well, I have those dots connected somehow together, or some of them don't have to be connected together. They have some inputs, outputs, like those spiders can be somehow mixed together, right? So what is this? Well, thanks to the fact how this spider is defined, thanks to this canonical delta, all that matters in this picture is which wires are connected together. So this is really like, if this was an electrical circuit, this is really like those dots, those are the nodes of the circuit where all the wires are connected together, and that's it, through this canonical delta. So this actually equals to, and here, well, I mean, this, and this, those are connected together. Then I have this thing here, I have this thing here, I have this thing here, and that's it. So I have some reduction rules in my diagrammatic category, which allows me to simplify the pictures. And in this case, it turns out that the reduced diagrams are just partitions. It only depends on how those k plus l points are partitioned together. So this is the set of all partitions of k plus l points. Well, actually not all partitions, because using these operations of tensor product, composition, and involution, I can only produce non-crossing diagrams. So this is actually the set of all non-crossing partitions. And if you fix the number of points, you know how many non-crossing partitions are there. That's actually the Catalan numbers. So from infinite number of diagrams, I have just finite number of diagrams. And it actually turns out that these two particular partitions already generate all of them. So that's quite easy to see that if you have k inputs and l outputs, you can do like k times this, and so on, and l times that, and you can produce any spiders. That's why this holds. So we've been able to describe this category using some combinatorial objects, using partitions. So that's good, because now we can work with this category somehow. Right, so this is just the summary of what I have written. By the way, well, I used as generators this m and beta this time, but it's also generated by these two partitions, but that's not so important. So yeah, that's nice. And now the question you might ask, well, okay, I know how many diagrams I have here. Does the number of diagrams really correspond to the dimension of the morphism space in the category. So in other words, did I figure out all the reduction rules, or are there some additional relations that I didn't tell you about? Well, I didn't tell you about one relation, which is if you compose like two spiders totally, like they can have arbitrary amount of inputs and outputs, but if you do such a closed thing with no inputs and outputs, the result is the number n, so the dimension of the original vector space. And that's it. And so, but aren't there some other reduction rules? Well, that's surprisingly easy to answer, because what you can do, well, what is the question? So I have here some category, let's say C, that's the category containing just the diagrams. And I am trying to interpret those diagrams as linear maps. So I have some functor from this category to the category of matrices or finite dimensions, vector spaces, or whatever. This is, by the way, called the fiber functor, but that's not so important how it's called. And this functor, well, what it does, well, it takes the diagram, the spider, and it sends it to, let's denote it by TKL, the linear map between the vector spaces. Well, and I'm asking, is this assignment, is this faithful? Or does it have some kernel? Well, what you can do is, well, maybe first of all, let's focus on this functor. This works for all the morphism spaces. So let's focus on diagrams with 0 inputs and 0 output. Well, this is supposed to be mapped to 1-by-1 matrices, right? So just the complex numbers. And is this faithful? Well, this must be faithful because, well, if you imagine any diagram with no inputs and outputs, you can always reduce it further and further, because you can, like, if you have no inputs and no outputs, you have something like this. I don't know, maybe like that. But you can contract those spiders together, and what remains you is, well, maybe there are some closed loops. So you count the closed loops. Yes, do you have a question?
So diagrams. Could you explain maybe one example of those two maps, mu and beta, how composition of these spiders and these spiders behaves? So, for example, how would it map to complex?
Yeah, so like you have this M, and you want to compose it, like for instance with this.
Well, yeah, but in terms of actual functions like delta.
Oh, right. Okay.
Yeah.
Right. So what might be the easiest example? So yeah, so for instance, okay, for instance, you can take this M. Well, first you can think of some two maps that are actually composable, right? So this multiplication, this is given by this chronicle delta, so its entries are just delta ijk. Do you know what I mean by that? And you could try to compose with, I don't know, for instance, this beta dagger. So this is, remember, beta was from B tensor B to C. So beta dagger, there's like a bivector. So it actually is equal to the sum of EI tensor EI, but you could also say that its entries are delta ij. Well, and if you compose M composed with beta dagger, well, remember that's M and now beta dagger. So you have 0 inputs, 1 output. So that makes sense, right? So this is a bivector, and you put it inside a multiplication. So this will have just one index, and the result will be sum over j and k, delta ijk, delta jk. So this is just equal to 1. And this is exactly what you obtain, because you obtain a spider with 1 output, which is given by canonical delta, but since there's just 1 output, it's just equal to 1.
Oh, okay, thank you.
Yeah, and with those loops, it's maybe slightly complicated. So if you would compose beta composed with beta dagger, what you would obtain is the sum over ij of delta ij times delta ij. So, well, you do sum over j. By summing over j, you kill those deltas, but you're left with sum over I of just ones, and that's why the n comes in. Good. Right, so this is how it works for no inputs and no outputs, and therefore this must be faithful. And actually, this means that if you study some, for all the others, it need not be exactly faithful, but we sort of essentially know all the relations. Why is that? Well, let me focus on 0 inputs, k outputs. That makes it slightly easier, but for the general case, it's analogous. Well, you are asking, well, this goes to B tensor k, and you are asking whether there is maybe some diagram, or maybe some linear combination of diagrams that's denoted by psi, and you are asking whether there is some psi such that if you map it, then this f of psi equals to 0. So, oh, well, what did I do? So 0 equals f of psi. Well, how can you tell that f of psi equals 0? Well, but you can compute this holds if and only if the norm of f of psi equals to 0. Let's say norm squared. Well, which is just f of psi dagger f of psi. But since you have this functor, you can write it as f of psi dagger psi. And since, but this already is a number, this is 0 inputs, 0 outputs, and we can see that, well, this has to be, has to be faithful. This is just a number. So this number, you can already compute inside the category just solely using the diagrams. you can have absolutely no information about the fiber functor to compute that. So you can characterize within the diagrams which morphisms must be mapped to 0. Okay, and you can just check that. What you can actually do is, well, you start, well, those diagrams as a vector space. This is spanned by the actual diagrams, right? So this is by definition the linear space given by formal linear combination of the diagrams. So you have some basis here, and you can just compute the Gram matrix by computing psi I dagger psi j or something like that. And well, if this Gram matrix, if it is regular, then you know that there is no diagram psi or no linear combination that would map to 0. If it's singular, then those vectors in the kernel must be mapped to 0, and that's it. So the kernel of this functor is just given purely by the composition rules of the diagrams. Right. And by the way, this matrix has to be positive or positive definite, because if it's not positive, then there can be no fiber functor, actually. So if it's not positive, you are sure there is no fiber functor. But now we know that there is one because we constructed it that way. Yeah, and somebody has computed those determinants and found out that this diagrammatic category, this description is faithful for all n greater or equal than 4. So actually we have faithful description of that. And what's that good for? Well, first application might be that every finite space for any n greater or equal to 4 actually has quantum symmetries. Why? Well, because let's go back. What does it mean that something has quantum symmetries? By this, I mean that this algebra here is actually non-commutative. If this algebra was commutative, then it means that since this is the universal algebra, then it means that any matrix with possibly non-commutative entries satisfying these relations here, any matrix actually must have, the entries of any such matrix actually must be commutative, because this universal C-star algebra already is commutative. So this is what we are asking. And well, or maybe I can stay here and asking whether this algebra is commutative. I can write it here, commutative, if and only if, and this is not an X, this is a diagram standing for the flip map. So this is like, this diagram stands for a map sending X tensor Y to Y tensor X. So the algebra is commutative if and only if inside the category contains the flip map. Because you can really write down the relation. What does it mean that U tensor U composed with the flip map? Maybe to make it clear, let's write it like T of the flip equals flip composed with U tensor U. If you write this down, that's exactly commutativity. You can, if you write down this in entries, it's really Uij times UKL equals UKL times Uij. So we can spot the fact that something has quantum symmetries just by looking at the corresponding category. And so what you can do is, well, this category with those diagrams with 2 inputs, 2 outputs, you can list them. So this is like this, like this, and so on. There are, I think, 14 of them or something like that. And if you compute the Gram matrix here, then it's not the determinant is non-zero. So mapping this to linear operators makes it faithful. And if you take this set and add the flip map to the set, then you can again compute the Gram matrix, and it's a determinant, and it is again non-zero. So this means that if you add the flip map, then this set remains linearly independent, and therefore the flip map was not a linear combination of those non-crossing things before, and therefore finite space has quantum symmetries. So that's one application. Second application is related to finite quantum spaces. So what is finite quantum space? Well, we follow the basic idea of quantum groups, which is the classical things are described by commutative algebras. So here we had the finite space. The finite classical space was described by this commutative C-star algebra and dimensional. And now what I claim is that if you take non-commutative C-star and dimensional C-star algebra, let's call that a quantum space, finite quantum space. And actually, for this to work, as I told you, you need some distinguished bilinear form, or equivalently a state on the C-star algebra, which makes it actually a Frobenius algebra. And you need some additional axiom to be satisfied, which makes it a special Frobenius algebra. It's not that important what that axiom is. The important thing is that if all this is satisfied, then this construction using those diagrams works exactly the same way as with the commutative case. And you cannot spot the non-commutativity because the flip itself is not an element of the category, so you cannot ask whether the multiplication is equal to multiplication with flip inputs. This you cannot ask this within the category. So there's no paradox in saying that the categories are the same. And so yes, the point is that since you can do the same thing, you obtain the same category, the same diagrams, and since we, as I already mentioned, since the kernel of the fiber function only depends on the category itself, if you have the same diagrams with the same rules, not only the diagrams are the same, but also the image must be the same. So again, if let's say n is greater or equal to 4, then any interpretation must be faithful, and therefore the categories described in the quantum symmetries are the same. You might ask the question, does this mean that the associated quantum group is the same? And the answer is no, because, well, if I go back here to this correspondence between quantum groups and categories, well, it is true that there's a one-to-one correspondence between quantum groups and categories, but the point is that the category we speak about, this should be concretely realized by linear maps. So in fact, you might say that this correspondence work if you, so it doesn't work with abstract categories. You might really realize this category by linear operators, or if you want, you have to equip your abstract category with a concrete fiber functor, concrete interpretation. Yes?
realize the category with concrete?
Sorry, I didn't understand. Can you ask it?
Correspondence is 1-to-1, but you also have to be able to realize the category in some way. How do you know if you can do that?
Yeah. So if there is no fiber functor, there is no quantum group. The category has to be this has to be a category of linear operators or an abstract category equipped with a fiber functor with a concrete realization. If you have just some abstract category, like you can take this category of partitions, and this sort of depends on a certain number, which stands for the dimension here. And you could theoretically, instead of this n, you can put any number and you obtain a category. But for some choices, there is no fiber functor actually. So there is no quantum group.
How do you know when there is no fiber functor, and how do you find the realization? Can you find, do you know it exists, but can you find it?
I'm not even sure whether you can tell whether it exists or not.
Oh, okay.
Right. So if, for instance, this is not what's called a C-star category, so if those Gram matrices are not positive, there cannot be any fiber functor. So there's sort of like a criterion. But if this is true, I don't think you must have a fiber functor.
Okay.
So
there's no easy way to determine if you have it or no, right?
No, I don't think there is.
Okay. Thank you.
Yes. So you need the fiber functor for realizing this as a quantum group. But in what I'm talking about today, we already always start with a fiber functor, so we don't have the problem that we did not have it in the beginning. So the quantum groups might be different, but they are what's called quantum isomorphic. And so you can take this as a definition. Two quantum spaces are quantum isomorphic if they have the same category, but similarly as this, as with this so-called Tanaka-Klein duality, this correspondence between categories and quantum groups, this quantum isomorphism again has a meaning sort of like quantum groups, and namely, if two things are quantum isomorphic, then there again must exist some matrix with, like you have symmetries, so automorphisms and isomorphisms. Like isomorphism is the same like automorphism, but it maps one thing to the other. So quantum isomorphism is the same, is like quantum automorphism. So again, this means you can construct a matrix with non-commutative entries, but this matrix will map you one of the quantum spaces to the other. So, right, I can write it down to make it more clear. So you have two quantum spaces. One has multiplication m, the other one has multiplication m prime, and you construct a matrix with non-commutative entries such that m composed with u tensor u equals u composed with m prime. And the same with the bilinear form. So that makes it interesting, I guess. Right. And you can study quantum symmetries of all sorts of things. But maybe it's worth saying that those finite spaces, they are interesting exactly by the fact that they have quantum symmetries. If you study continuous stuff like quantum symmetries of a sphere, let's say, you will always find out that it has no quantum symmetries. So the phenomenon that classical things have quantum symmetries, this occurs in those discrete cases. So this is what makes it interesting. You can, for instance, also study quantum symmetries of graphs. So a graph is like a finite space, but it is equipped in addition with an adjacency matrix. So you're sort of studying this category with some extra, again, black box denoted by A. And now the elements of this category are something like, well, those are the spiders, but except for the spiders, you also have those A's somewhere. I don't know, something like that, maybe put the A also here, and maybe like that, and so on. So those are the elements of this category. You can slightly simplify your notation by, well, deciding instead of this box with A, I make a thick line as I wrote here, or since, well, writing that by hand, it's complicated to write thick lines, so maybe red lines. So maybe the elements would then look like this. So red line then stands for the adjacent matrix. So it's like these diagrams. But now the point is, what's not so convenient is that this adjacency matrix can be anything. And you have no sort of reduction rules for this adjacency matrix. So you can never be able to find a faithful diagrammatic calculus that would cover all graphs. And that makes sense, because otherwise all graphs would be quantum isomorphic, which is not true. So this diagrammatic calculus is useful, but it is not that useful as for the case before. Did I want to say no? But what you could try is developing some diagrammatic calculus for some special class of graphs or something like that. But in any case, what I did was I studied Hadamard matrices. So you might know Hadamard matrices. Those are matrices with ±1 entries, and all of the rows and columns are mutually orthogonal. Equivalently, it's up to normalization, a transformation matrix between two bases, which are self-conjugated and mutually unbiased, which what I mean by that is that if you compute the inner product between the elements of the two bases, you always obtain ±1/n, which is exactly this condition, ±1s as entries up to the normalization. And now the classical notion of equivalence of Hadamard matrices is a bit more complicated. So that's the reason why if I study quantum symmetries, I'm not just putting the Hadamard matrix in my category, but I must do it in a more sophisticated way. So two Hadamard matrices are equivalent if you can map one to the other by permuting rows, permuting columns, multiplying rows by -1s, and multiplying columns by -1s, which might be slightly complicated to capture. So yeah, so well, I probably, in any case, I don't have much time to explain the details, which are just technical computation, so it's not that interesting, I suppose. But the resulting category to capture these equivalences looks like this, where this is the spider we know. Notice that instead of one input and two outputs, we have two inputs and two outputs. So as a result, within this category, you have only spiders with even number of inputs or outputs. That's so that's making this category a bit smaller, but you have two kinds of spiders. And those two kinds of spiders somewhat stand for the two kinds of, these two bases. So this is like chronicle delta in one basis, and this is like chronicle delta in the other basis. And you can point out that, well, if the two bases are self-conjugated, so the transformation matrix is real, then this must work. And the fact that they are mutually unbiased, so computing the inner product from one basis to the other gives 1 over n. This is this relation. Somehow, I know that, well, I'm not saying it's obvious, but you can compute that. And you can figure out the reduced diagrams. So as I said, all the inputs and outputs are, or the nodes are of even degree. Well, since two spiders of the same kind can be constructed, the resulting diagram is a bipartite graph, and that's more or less it. And again, it's planar. And again, you find out that this description is faithful, because if you consider diagrams with 0 inputs and 0 outputs, those are those simple planar bipartite graphs with vertices having even degree, not equal to 0 or 2. There is no such a graph, and therefore reduced diagrams are just numbers. And this is how I proved that, well, this is using that you can do the same thing as I did with, as I illustrated on this simpler example with the partition category and finite quantum spaces. Every Hadamard graph or every Hadamard matrix of a size at least 4 has quantum symmetries, and any two Hadamard matrices of the same size are quantum isomorphic. So that's what I did, and I don't know if there is a question, or maybe there will be questioned afterwards. And in the last couple of minutes, I just wanted to list a couple of questions, like directions for further research that you might also be interested in. So let me do that. So some open questions related to quantum symmetries that's, yeah, I think might be interested in this audience. First question about duality of association schemes. I was inspired to this question by a discussion with Chris Gotzel. I'm not sure if he is aware of this discussion at all, because it happened on Math Overflow. So I was asking some questions and question, what is this kind of duality? And he answered, well, this is the duality of association schemes. But this is not important for this. This story is not important for the question. So I've read something about duality of association schemes, and it really reminds me. It really reminds me, but I'm not sure if I'm correct. So that's my question on you, actually. It really reminds me the duality, the Pontryagin duality for groups. So if you have a group, you can construct its Pontryagin dual, but this only works for abelian groups. And, well, if you have, well, it's just some construction. And if you do it twice, you obtain the original group again. And this is one of, if you open a textbook on quantum groups, this is one of the motivations, because classically the original group has to be abelian, because, well, if you know something about quantum groups, you have, in quantum groups, you have two kinds of multiplication, the multiplication and the co-multiplication. And now one of that sort of encodes the multiplication of the group, and the other one is the sort of like the topological multiplication, which is for groups always commutative. Groups are characterized by this multiplication being commutative. And this Pontryagin duality switches the multiplication and co-multiplication. And that's why the people that were studying this classically weren't able to construct a dual of non-abelian group, because the dual of non-abelian group is not a group, it is a quantum group. That's the point. So if you generalize this to quantum groups, then it works perfectly nicely. Dual of a quantum group is again a quantum group. If the first one is abelian, then the other is actually a classical group. If the first one is a classical group, the dual is abelian quantum group, and so on. So this works really nice. And my question is, well, what I've read is that this duality for association schemes works nicely for abelian association or commutative association schemes. Couldn't it be that if we introduced quantum association schemes, one could extend this duality and have something like this Pontryagin thing there? So this is my question. Maybe it doesn't make sense, maybe it does. I think this would be really nice if this was true. So this is my first question. Second question, well, this is maybe slightly more technical, but well, I've been studying these categories, this category, which is, well, if you checked this article, this was called the NC bipart even, and this I called the NC bipart. So here I have those bipartite graphs, and here I have the additional restriction that all those graphs are of even degree. And why do I study this category? Well, because here I don't have enough reduction rules. But maybe we could add some reduction rules, and maybe then these two categories would be interesting. And I think these are interesting reduction rules, which basically means that instead of studying Hadamard matrices, you are studying some specific Hadamard matrices, namely these Fourier transform, like those Walsh matrices. So including these relations, you would study only these Hadamard matrices. Or you might say that you are basically studying this group. So here you would obtain quantum automorphisms of this group, actually. But it is not that hard to find out that this is actually classical using this thing. But what about this? Maybe does this contain the crossing or not? That's an interesting question, I think. And this would correspond to some affine transformations on this Z2 power n. So this is also what I find interesting. And maybe you could also construct some graph whose quantum symmetries this is. So this is what I find interesting as well. And maybe last thing that I wanted to ask, well, it would be really nice to determine the quantum automorphism group of those Hadamard matrices. So we know that this is not a classical group. So what kind of quantum group that is? And to start with, my question is, what is the automorphism group of Hadamard matrices? Well, I'm not sure if I'm asking the correct audience, because you're probably not group theorists, so I don't know. But this would be where I would start. And I don't know, does this have any structure? Again, you can start with the simple example of these matrices. Those are the canonical Hadamard matrices, I would say. I discovered some clues. In the Sloan database, the order of the largest automorphism group. So if you list the order 2 to the power n, which corresponds to this example, those are these numbers. And those exactly appear also in this sequence, which makes it interesting, maybe. And this sequence appears in this article, and this is a sequence of orders of some groups of exactly this affine self-dual group. So maybe this affine self-dual group is the automorphism group of Hadamard matrices. Would make sense, I guess, but I'm not sure. I'm not fully understanding this article. So, but I think this would also be interesting to study. And if you have anything else, I'm open to any discussions, whatever. So I noticed that you studied also those quantum walks on graphs. So I was always wondering whether quantum symmetries could play a role there or not, but maybe that doesn't make sense. I don't know. But that's more or less it.
Okay, thank you, Daniel. So, any question for Daniel? Bill, do you have a question?
I think I have a question. So I think in the abstract you say that well, first you've shown us that all finite quantum spaces are isomorphic. Now I think you said in the abstract that all finite quantum spaces correspond to Hadamard matrices. Can you elaborate on this?
No, I don't think, or maybe maybe I didn't write it correctly, but what I wanted to say is, in the abstract, is that I'm going to illustrate this on this example of finite spaces, but yeah, but that's it. And you can construct also quantum Hadamard matrices or on quantum spaces. And again, you can extend this result in this direction. So then not only all Hadamard matrices, but also all quantum Hadamard matrices of a given size are mutually quantum isomorphic.
I apologize. I misremembered the abstract. I just read it just now. Okay, thank you.
Ada, do you have a question?
Yes, I do. Thanks for the talk, Daniel. It's very interesting. So when Bill and I looked at the Hadamard graphs, we picked the Hadamard graphs because of the connection to spin models. I'm just curious that why did you think that would work for Hadamard matrices? Where it came from your.
You mean what was my motivation?
Yeah, why did you think that there would be quantum symmetry among Hadamard matrices at the same size?
Yes. So, well, what I did is that, well, I first discovered this category because I wanted to do something else. What I did, I wanted to construct some quantum analog of coxeted groups of type D, and this is what I discovered. But after all, this direction didn't make much sense. But then I opened the textbook Picturing Quantum Processes from Bob Köke and Alexander Kissinger, and I noticed that they exactly study this category that I discovered. So, and that it is related to Hadamard matrices. So I realized that it somehow describes Hadamard matrices in some way. And actually it turned out that it exactly describes the symmetries of Hadamard matrices. So that's how I studied, well, what I did. So I didn't want to study them beforehand, just appeared there.
But you mentioned that they are the transition matrix between mutually unbiased spaces. How much of it does it play a role in the quantum, in the two Hadamard matrices being quantum isomorphic?
How much does the fact that the two bases are unbiased?
Yeah, it's a transition matrix. Every Hadamard matrix is a transition matrix.
Yeah, well, I think this plays a role when constructing the category. So you could do Well, I'm not sure if this would make sense for some general matrices. Like, I mean, would the classical notion of equivalence make sense for arbitrary matrices? Probably not, right? But what you could study are complex Hadamard matrices. So if this was not self-conjugated, that might be interesting. But then you wouldn't have the equality here, which would make it complicated. I think I didn't think about it too much in detail, but that would be maybe also an interesting direction for further research.
Thank you.
Following up on that, I mean, if I just replace a Hadamard matrix by a unitary, if I had two unitary matrices A and B, can I find a U such that UA equals BU? Is there anything that's going to be a coarser refinement of the unitary group than just the commutator algebra? Or I mean,
okay, so you're saying that you'd have
UAU dagger equals B. This is what similar unitary matrices, but maybe some non-similar matrices would have that equation hold true when U is allowed to be a quantum matrix, an element of the quantum unitary group.
Okay, well, that's interesting. Maybe yes. Well, at least, well, this is exactly what you're studying with quantum symmetries of graphs, right?
Yes,
but here you have the additional restriction that these matrices have to be permutation matrices or quantum permutation matrices. So you were asking whether it would make sense to study that for general unitary matrices.
I'm trying to get at your answer to Ada's question. Why were the Hadamards? Why did the Hadamards stand out as particularly interesting unitary matrices to you? Why not just an arbitrary pair of unitary matrices?
Yeah, why it's interesting for me? Well, as I said, I didn't study it before. I wanted to study Hadamard matrices. They just appeared themselves, I would say. But yeah, why not? You could try. But the point is that, well, you need to figure out some class of matrices that would be somehow quantum isomorphic to make this interesting. So you're trying to figure out some class of matrices such that you are able to construct this diagrammatic calculus and have what I called enough reduction rules. So you have to have enough information, enough relations that are satisfied by your class of matrices, such that you can work with the diagrams in some interesting way.
There's a question in the chat from Dave Robson.
Okay, let me. No, I don't. So that's an interesting question, whether the quantum automorphism can be. So this only proves that there is a quantum isomorphism between any pair of Hadamard matrices. So there is a matrix with non-commutative entries that would satisfy all the relations that I actually didn't write down here. But yeah, but it could have. But this proof isn't constructive, so we don't know any example except for, well, writing down again the universal C-star algebra satisfying these relations, and well, this universal C-star algebra must exist and satisfy these relations. But the question is whether we can construct something like constructive, like something like taking some usually Hilbert space and some usual construction. In particular, whether we can find some finite dimensional representation of that algebra, but that's still an open problem.